Hi, so I'm going to be talking about interpolation of data and how you might go about doing it. So, interpolation is the generation of new data using existing data. It has lots of applications, including filling in missing data values, smoothing out irregularly spaced data, visualizing data, and synthesizing new data. So, I've written some code here to show you what some of the one-dimensional methods look like first. The initial data set in this case is x and y, shown here, where x is just 1, 2, 3, 4, 5, and y is 2, 4, 1, 3, 5. Then I would like my interpolation function to predict the value of y if x is to equal the numbers 1 to 5 in steps of 0.1. We'll go and run this now. One-dimensional methods will try to fit a curve based on the given data using different algorithms. I won't get into how these work, but you can see that different algorithms fit their curves differently, and which one you choose to use depends on the problem you're facing or the type of data you're trying to get out of it. However, more often than not, datasets are more complicated than the plots you just saw. For this reason, I'm going to take you over to a three-dimensional data example and try to help you visualize interpolation in higher dimensions. So for multi-dimensional data, instead of fitting a curve onto given data, interpolation functions will fit something called a hypersurface instead, which is essentially a multi-dimensional surface. We'll need to prepare a few things to show this example. So firstly, I have three vectors, x, y, and z, where x is 1 to 10, y is 2 to 20, but in steps of 2, so it'll only be even numbers, and z is 5.5 to 10 in steps of 0.5. And each of these have 10 samples. So then I convert these into gridded coordinates, which are called capital X, Y, and Z. Then my function A will be sine of X plus cos of Y, all multiplied by Z. By working with gridded data, we are basically evaluating A at every possible coordinate. To visualize what A looks like, we'll use the slice function. The slice function takes our results for A, which has a value for every point in space within this block. We can look at slices of this three-dimensional space to see what coordinate values of x, y, and z corresponds to large values for A, indicated by the brighter colors. For instance, on this point here, we'll go ahead and evaluate that in the command window. So that'll be sine of 9 plus cos of 10 all multiplied by 10. That gives us 11.4. But if we go to the other end, where the colors are much darker, like this dark blue here, we can go ahead and evaluate that too. So x is 1, y is 10, and z is 5.5. And you can see, relative to all the values for A, this corner gives us much smaller values. So carrying on then, knowing our existing data now, we can interpolate the data between our points. We'll create what is known as a query grid, which is xq, yq, and zq here. And that will tell the interpolation function to predict values for A at these points. These points will have the same range as x, y, and z, but they have a smaller step size between them. Now we can bring all our data together to predict values for A on our query grid. So we'll go and run that now. And we're visualizing these in the same slice plots. So you can see the trend in magnitudes to be similar, but the figure on the left just has far more sample points. Now, looking back, it seems that we could have just evaluated AQ the same way we evaluated A. But if we only had values for A and not the actual formula for the function, then we would in fact have to resort to interpolation or some sort of prediction method. Now, hopefully, you have an idea on how to interpolate one-dimensional and three-dimensional data and have an idea of what it might look like. Thank you.